Yeah, so hello. Let's start the session for today.
Good evening, ma'am.
Yeah, good evening. So, today, let's briefly go through the charge transfer complexes first. And there are two problem of the same concept. So, I will just play one video now.
Hello everyone. In this video, I will be solving date 2017 chemistry question number 10. This question states that the complex vanadium oxide, chromium oxide, and manganese oxide ion exhibit intense ligand to metal charge transfer transition. The wavelength of this transition follows the order. So we are given that these exhibit ligand to metal charge transfer, and we have to find out the order of the wavelength of the transition. So before that, let's move into some basic. So the charge transfer transition denoted as CT. So the question is that why is it that some transition metal complex are intensely colored in solution, but possesses no d electron. So we know that there is a possibility of dd transition and it shows color in the complex. So if there is no electron in the d orbital of the metal, then what is the reason for the intense color for a metal complex? For example, KMnO4, where manganese has a oxidation of +7 and with the electronic configuration of 3d0, so there is no electron in the d orbital. So it declined the fact of dd transition happening here.
If it's going too fast, you can tell me. Okay, otherwise, I have just increased the speed a little.
But instead of that, it still shows a intense color, KMnO4, like purple. So there are things that we have to note here that the vacant metal d orbital is a very good acceptor here and can accept the electronic charge density from the ligand system or any oxide system, correct? Because because my d orbital is empty here. In transition metal complexes, change in electron distribution between the metal and a ligand give rise to the charge transfer CT bands. Okay, and these CT absorption these lie in the UV regions and are intense and they where the selection rules are actually allowed. So these have a silent value of up to 50,000 or greater. Okay. Yeah, but in the case of where only DD transition is happening, we see that the delta E is very small for the transition to take place. So when the delta E is very small, the epsilon max value is also very less than or equal to less than 20 liter uh, This is also less than 20 liter molar inverse centimeter inverse. So this gives me the points where for good detection, I should actually take a very high concentration solution for this or even a higher path length of the cell. Also, this DD transition shows a very less intense color because of the selection rule forbidden DD transition. This result in a weak absorption. However, in the case of the CT transition, we detect it is very detectable in a low concentration of the analyte also, following the law of Beer's-Lambert law, where absorbance is equal to silent, B is the path length, which is generally 1 centimeter, and C is the concentration. So in the case of CT transition, it is possible to detect even the low concentration because of the epsilon value, which is Emax, is very high, that is up to 35,000. So the charge transfer transition, particularly for the LMCT, if we talk about, it is from the metal line, and it is in between the metal line orbitals and the ligand orbitals. So the metal line, when it is in highly oxidizing state and my ligand is in reducing state, then this will be referred to as, this case will be referred to as ligand to metal charge transfer. And the example for that, as we have discussed, KMNO4, where my O2 negative is highly reducible, and the intensity of the color is due to the fact that there is a high probability of these transition taking place. And the example are mercury I2, which is brick red in color, and CrO4 2 negative, which is yellow in color. And the charge transfer transition, the CT transition, are actually classified into metal to ligand charge transfer, so MLCT, or ligand to metal charge transfer, or LMCT. There are other two categories also where there is two oxidation state of metal is present. So it will be a metal to metal orbital, and if there is state of ligand is present, then it will be a ligand to ligand. But here we will focus on the LMCT first. So the ligand have actually the sigma antibonding, pi antibonding type of orbital, also non-bonding orbital, molecular orbital. So if the ligand molecular orbital are full, so the charge transfer may occur. So the charge transfer may occur from the ligand molecular orbital to the empty or partially filled metal d orbital. And for some example I have given here. So for LMCT, very common for coordination compound having pi acceptor ligands. So these are the example of pi acceptor ligands. So in terms of molecular orbital, let's look into. So this is a D6 uncoordinated metal. So D6, okay, and here we have a ligand where it's a sigma orbital, for example. So this is a full sigma orbital. So in octahedral complex, my molecular orbital of the given complex will look like this, where the splitting of degenerate d orbital take place as in octahedral field, following with splitting in T2G and EG orbitals respectively, and then the charge transfer LMCT will take place from sigma orbital here to the one which is empty. So it will be something we can. This is sigma antibonding for it. Okay, so this will take place from the full ligand orbital to the empty metal orbital. So this is the LMCT, and so this will be the energy or the wavelength associated with it will be observed as in the absorption band. Here you can look into this figure where this T2G and EG comes from the metal. Okay, and my EG acts as a sigma antibonding here. Also, the transition that I have shown here is from the sigma. It can actually take place from either sigma or pi to the antibonding of sigma antibonding or pi antibonding. So, for example, here transition can take place even from the full pi orbital or full pi antibonding to the EG sigma antibonding, correct? So coming to our question, which was asked, that these given complexes, we should find out the order of the wavelength of the transition for the LMCT. So for LMCT, so we have to find the wavelength of the given transition. So before that, we have to note that as the Z effective increases, so Z effective is the charge between on my metal orbital, so it is a nuclear charge. So as it increases, it will attract more the ligand orbital, correct? And the so my energy order will be So ligand will act as a donor and my metal will act as a acceptor. So so the oxidation state is as follows: vanadium plus 5, chromium plus 6, manganese plus 7. So you can see that the molecular orbital will look like something for the Mn. So this is, if it is my Mn plus 7, so my ligand is here, okay. And for chromium, it will be a little higher. And for vanadium, so overall, the transition from ligand to metal, the energy order will be, so the energy order will be highest in vanadium, and then chromium, and then manganese. So this will be, the energy order is, okay. And as we know, my energy is inversely proportional to wavelength. So the order get reversed in the case of wavelength. So my wavelength order will be this. So the correct option for the given question is option number C. Okay. And I will refer you to go through the lecture, Charge Transfer by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link is attached. Thank you.
Okay, so if you guys have doubt, you can ask. Otherwise, I will move to the next problem of the same charge transfer complex. Okay. So this is a 2015 problem. So this question number 23. Yeah, okay. I think I was muted that time. So now if you can hear me. So shall I start? You can hear me, right?
Yes, ma'am.
Okay, good. So this is a question from 2015, and this question state that the intense red color of this particular complex is due to. So since this is a ligand, you know, this is bipyridine, and this complex, so bipyridine, this is a strong field ligand first of all, and it's a neutral ligand, and it's a pi accepting ligand. Okay, so these are the things you should know whenever you see a ligand or a metal complex. You should you should be aware of what are the properties of that particular ligand of making that complex.
Ma'am, please repeat the properties of ligand again.
Yeah, so this is bipyridine. So it's a strong field ligand, it's a neutral ligand, and it is a pi accepting ligand. Okay, so don't worry, we will go through it again in when I will be discussing the detail. and we are given with four options, that is the whether the intense color is due to MLCT, due to LMCT, that is ligand to metal or metal to ligand charge transfer, or simply the DD transition, or the intervalence charge transfer. And since you have gone through the previous video, I hope you get to know that the DD transition doesn't give that much of intense color, although the MLCT and LMCT does give you that. And about the intervalence charge transfer, there must be two valence metals or ligand should be there, so that there is a intervalence charge transfer. However, in our case there is no such type of two valence of this metal is there present, so D option is already out of our scope. So now let's quickly go through the concept. So the particular problem that I have in my hand, so since you have gone through the LMCT charge transfer in the previous video, so in this I will only be discussing what is the metal ligand charge transfer, and I hope you will understand the difference. It's very simple. So let's quickly go through the MLCT charge transfer, that is the electron transfer from the metal d orbital to the pi antibonding orbital of any orbital of the ligand. So here there are I am giving you two examples, that is bipyridine and CO. These two are the pi acceptor ligands, and hence they can accept electron from metal d orbitals, okay, to their pi antibonding orbitals. Also you have seen this type of back bonding that we have called in our previous live session. So that was also a metal to ligand charge transfer, okay, that was what we called as a back bonding. Now the metals are in lower oxidation state in this case, because we want more electron rich species so that it can donate from its d orbital to the ligand, okay. So keeping this in mind, that the metal is in lower oxidation state, and the ligand are pi acceptors. Since CO is a pi acceptor, this bipyridine is also a pi acceptor, okay. So now often there is it's a property that often this transition take place, and it's in a higher energy range, and that is what we say, it's in a UV range, okay. Now coming to our complex, what was given to us, so we are given with this complex, and since it's a neutral ligand, so the charge is 0 there, and the charge on Fe, that is my iron, will be +3, okay. So my iron 3 plus this metal, iron 3 plus electronic configuration become argon 3d5. Now the bipyridine is the strong field ligand, okay, and I have 3d5. Now when the splitting happens of the my d orbital, because since it's a octahedral complex, so in octahedral field the splitting will happen in a manner of T2G to EG, okay. And since it's 1 2 3, so and since it's a strong field ligand, so it's a low spin complex, okay. And you can see that the pairing is there, okay. And the ligand pi antibonding orbital will be such that it will be lying above, just above EG, and hence we can say, we can see the metal to ligand charge transfer in a manner like this, okay. Here please note that the DD transition are forbidden here in this case, but it can, I have read it that it can also be observed in some cases, so I am not sure about the examples, so let's skip that part for now. So yes, let's get back. So our correct option was option number A. That was you look into the property of the ligand that you have and the metal that you have, the oxidation state, whether it is higher in high oxidation state, in low oxidation state. And yes, so the correct option that was that defines the intense color of my complex is option number A, that is metal to ligand charge transfer. So any doubt? Okay, so I will continue. So this is again a 2015 gate problem. So this question state in that the absorption spectrum of this given complex in solution comprises of maximum with a shoulder. Okay, so the reason for the shoulder is, so okay, so we are given with option where we can see there is a charge transfer between the ligand to metal, metal to ligand, and there is a third option which is Jahn-Taylor distortion, and the fourth is the nephroxotic effect. Okay, and I think I have already discussed this nephroxotic effect in some of my tutorial video, so I'm not going to explain it again, but this is yeah, okay. So let's go and find out what is the how the absorption spectra of this complex is turning out, and what is the reason for the broadness or the shoulder that we are noticing in our absorption. Okay. Yeah. So this problem 19 from 2015 gate is that we see that we have to see just the electronic spectra of the given complex we have with the titanium. Okay, so again finding out the oxidation state of our metal, that is titanium here. It's since my water is a neutral ligand, so I have the charge whole alone on my metal, that is +3. So my titanium 3 plus. Okay, and the electronic configuration I can write it down simply as the argon 3d1. Okay, now looking at the electronic configuration, it is very simplified. I have also discussed the orgel diagram in one of my live session or in one of my solution video, so you can check that out. What is orgel diagram? I am now here just applying the concept of it. So first of all we have to find out the term. Okay, and corresponding to that term we just draw simply the orgel diagram and find out the electronic transitions or the transitions that will happen for the absorption. Okay, so the term for this titanium 3 plus will be, so this is my d orbital, and since there is only one electron, so I have represented it here. So my L will be equal to 2, that is corresponding to capital D term. Okay, and my spin, that is small s, is equal to half, and 2s plus 1 will become 2 into 1 by 2 plus 1 equal to 2, and therefore my term become 2D. Okay, so now this complex is octahedral since we know. Okay, where is it? Yeah, so it's octahedral, and we know the term also, so we will draw the orgel diagram for the given term. Okay, so you see that in the orgel diagram itself we see a single one absorption band which will be observed because of the transition between the T2G to EG. Okay, so here the note is that one absorption band is observed. So this absorption band is appear around 20,400 centimeter inverse. This is the wave number, okay, quantity. And also you can find out the, I'm just giving this extra, that you can find out the energy corresponding to that absorption, okay, particular. So this is n into h, that is my Planck's quantum number, this is my Avogadro number, this is my velocity of light, and this is my this wave number corresponding to that transition. Yeah, so this you can find out. Other than that, so in aqueous solution this complex is blue or purple in color, and that is due to the dd transition that take place between the two metal orbital, d orbital, okay, that is between the T2G to Eg, correct. And that is the reason for the color for the solution. But our main concern was about the shoulder that we are experiencing in our absorption band. So that you can define, or you can explain due to the so in our octahedral complex, my, so this was my titanium 3 plus, which was basically giving me argon 3d1 configuration. And as you write it down here, so this is my 3d1. So once, since it is a octahedral, in the octahedral field it splits in between the T2G and EG orbital. You see that there is a unsymmetrically filled T2G orbital, and because of that you will experience this metal complex will experience a Jahn-Taylor distortion. This is also I have discussed in my previous live session, Jahn-Taylor distortion. So this is the main reason for the broadness, and due to this there is a shoulder that is in the absorption band of the complex, okay, and hence this is my correct option for the given problem. So option number C, that is my Jahn-Taylor distortion, is the is the correct answer for this problem, okay. Yeah, so if you don't have any doubt in this, I will move to another problem. So this particular problem from GATE 2014 chemistry, question number 42, I think among the following, the complex ion that is expected to show the highest magnetic moment at room temperature is. So we are given with four different metal complexes. So in these metal complexes you have to find out the magnetic moment value, and that you can find out from this particular formula, that is mu, that is my magnetic moment, is equal to under the root n. So wait, yeah, n plus 2 there, wait, okay. So this you can find out from this particular formula, and we will do it in yeah, so we will do it here. So the magnetic moment for the given complexes, for the complex number 1, that is my nickel cyanide, okay. So this is a tetrahedral complex, as you can see, and you will find out that the electronic configuration is 3d8 here, okay, and 1 2 3 4 5 6 7 8, and since my cyanide is a strong field ligand, it does the pairing of the electrons of the nickel, okay. And further sorry, so the further uh, ligand electrons from cyanide, so there are 4 cyanide, that is 1 2 3 and 4, okay. So this is the ligand electron in red color, and for we will do this first, and then I will find out the number of unpaired electron corresponding to each metal complex. Okay, so simply writing it down again. So here this is my 3D, this is my 4s, and this is my 4p. And since this is my iron, so it has 3d5 configuration, and you can write it down like this. Okay, now I have already done the pairing due to the strong field of cyanide present. Now for the third complex, that is my copper H2O 6. One, two, three, four. Okay, I need. Okay, so this complex of copper, this will again have 3D, I think 8 configuration. So okay, and for cobalt, now in red color, just donating the okay, these red electrons denotes the ligand electrons. Okay, and so from copper, oh, so there will be one electron here from copper, and the rest are the ligand electrons. Similarly, these are the ligand electrons. Now the number of unpaired electron for this, unpaired electrons are 0. For iron, unpaired electron is 1. For copper, unpaired electron is again 1. For cobalt, it's 0. So now I have told you in the last live session that you can do it by yourself, and then we will discuss that why between these two, yeah, so why between these two, iron and copper, we have a correct winner. Here the correct option is this iron complex. So any of you can answer this, like, because both of them have the same unpaired electron, n is equal to 1, but the correct option can be only one of them. So why the correct option is iron and not copper? Okay. So it's simply you can understand it something like this, that more the unpaired electron, so the magnetic moment is generated due to the unpaired electron. Okay, and the more the unpaired electron is closer to the nucleus, more will be the magnetic moment of that particular compound or the complex. Okay, so now here, since you can see in the configuration of these two, iron and copper, these two configuration, that you can see that the unpaired electron in the iron case is more closer to the nucleus than in comparison to the copper. Okay, so in this particular case, that is only one reason that you can give, and that's why we choose the correct option as B. Okay, so I think it's clear. uh, so any doubt? So okay, so this is a numerical problem that I will like you to first solve with me, because I am also trying my hands on this, but I didn't get the correct answer, which is, so you can help me in this. So this is the 2015 problem, that is question number 36. So this says, just you can take your pen and copy and then solve it with me. Okay, so the difference in the ground state energy, so we have to find out the difference in the ground state energy, and that too we have to find out in kilojoule per mole. Okay, of an electron in one dimensional box of length 0.2 nanometer and 2 nanometer. Okay, so write down the length, that are the difference of the two length is 0.2 and another one is 2 nanometer. Okay, so that particular problem that we had, so for a for the energy of any nth energy level, I can write down for my one dimensional box with length capital L is, that is En is equal to n square h square upon 8 ml square. Okay, now uh, this small n is the number of energy level or the nth energy level, h is my Planck's constant, m is my mass of that particular particle. Here we are talking about electron, so we will take mass of electron. L is my length of the box, and it was given to me for my two one dimensional box, so I'm describing it as box 1 and box 2, and this is as L1 and L2. So my L1 is 0.2 nanometer and L2 is my 2 nanometer, and my L1 is 2 into 10 to the power minus 10 meter, and my L2 is 2 into 10 to the power minus 9 meter. Okay, so I have just converted them into meters. Yeah, so I took the difference between the energy, that is my box 1 having length L1 and box 2 that is having length L2, and so I have taken the common from both, and that is n square h square upon 8m, and the difference is 1 upon L1 square minus 1 upon L2 square. Okay, so E1 minus E2, just put the whole value of like Planck's constant we have. Okay, oh yeah, 8 into 9.1 into 10 to the power minus 31, and these are the two values for both length. So yeah, while I was calculating, I think I didn't take the square of my Planck's constant, so I will calculate it just right now. So if any of you have calculated it or calculate, then you can give your correct numerical value in the chat box. Okay. So this will be 0. So this comes as joule. Now since I want it for kilojoule per mole, okay. mm, so the Avogadro number should be multiplied, so this will be so. Is it clear to you, Shikha and Gunasli?
Ma'am, we'll check after class.
Okay, after class. Okay, fine. So it's simply, I think, you have to take account of the units conversion, and you have to take in mind what they have asked about. Since so Gunasli is saying that it's 10 to the power minus 29. 29. So Gunasli, where you are saying that it should be 29? Here. Um, no, actually, The correct answer is also in the range of 896 to 900. So I think you have to check out. Okay, so you are saying that I have done a mistake. So I see, so the 9 minus the 19 that is coming there, minus 19 that is coming there is from here. Okay, so this 32 into 2, that is 68, and this minus 31 will come up and that will become plus 31, and this whole will become minus 37. And since I will take 10 to the power 18 as common, so here will be 100 minus 1, and this will be 37 minus 18 will give me 19. Yeah, okay. Okay, so this is some simple numerical, but you have to keep in mind what they have asked, since we get energy difference in joule, and then I have converted it into kilojoule per mole. So I have divided it by 1000 and multiplied it with the Avogadro number. Okay, yeah. Now getting back. So since I have added these two problem here, okay, so you can just I think just keep this in mind, okay, because I think maybe you have solved it, or if you have not solved it, just keep in mind that from where the question have been asked. So since this is a Langmuir absorption isotherm problem that they have asked about, if theta denotes the surface coverage. So if theta denotes the surface coverage and P denotes the pressure, the slope of the plot of 1 upon theta versus 1 upon under the root P is. Okay, so I think both of you should write it down, that what they are asking from the Langmuir absorption isotherm. Okay, and try it. If you don't, if you are not able to solve it, then you can mail me today only, or as you get the time, because since you have your paper on 5th February, I think, so you should not leave any problem now. So this is one, okay, from Langmuir absorption isotherm. So I think it's pretty simple if you see the plot. So I have not included all that here, so if you are not able to solve it and not able to get the correct option, okay, then you can mail me. Okay, and this is another problem, that is the gas phase unimolecular reaction at temperature, that is my room temperature, with the pre-exponential factor given to me. The entropy of activation is. So try this one out also. If you are not able to do it, then you can mail me. Okay, also there was one another, yeah, so this is from GATE 2014. So I'm just introducing all the problem that I have in my PPT right now, because I think this one will be the last live session we have. But anyways, you can just simply mail me if you have any further doubt. Okay, so magnesium 2 plus is preferred in photosynthesis by chlorophyll because, so yeah, so these were the 4 options. So wait, so any of you know what is the correct answer for this? So the correct reasoning for the option number, so the correct option given was option number B. Okay, that is, it has a weak spin orbit coupling, and the reasoning was given is that the chlorophyll preferred this magnesium 2 plus because of this small spin orbit coupling, and due to this it have so the intersystem crossing is inhibited because of it. Okay, so this favor that the energy transfer will happen from the excited singlet state. So this was the reasoning given. I am just actually I'm not able to very much understand the concept because I have to get into deep into this chlorophyll mechanism and all. So, but I find out that the correct reasoning was given like this. So I think I tried to give you as much as problem for today from today's live session. So yeah, that's all I have. So I have discussed, I think. So you guys have wrote down the key points that I have told you from this and this. And if you have any further doubt or even apart from this, you can ask me. I will try to solve it. Okay. So you have your paper on 5th, right? Yeah, Shika.
Yes, ma'am.
Okay. So all the best. So I think this will be the final live session. So all the best to all of you.
Thank you so much, ma'am.
Yeah, okay. So I think that's all for today's live session. Thank you for joining.
Ma'am, share your email ID.
Yeah, so my email, I will just write it down in the chat box. Yeah. Okay.
Okay, ma'am. Thank you.
Yeah, okay.